Hello, folks. So this is what happens when you type in google.com into your search bar and hit enter. So Aditya and I will be presenting. Try to mute your mic if you are not talking, but feel free to unmute your mic. And like when we used to give this in person, we actually gave this in person a couple of years ago when we were still students. We didn't have slides. It was much easier to just use a whiteboard. But when we gave it in person, people just interrupted it all the time and asked questions, which is how it should go. So feel free to unmute your mic, turn off or unmute your video, and ask a question at any point. Cool. Right. So
let's start by introducing
screen,
ourselves.
Right? So can you guys see the screen change?
Yep, all good.
Yeah.
Neat. All right, so Sean made these slides because I'm lazy, and Aditya and I are going to give the talk. So about the speakers, so I'm a production engineer at Facebook right now, based in Menlo Park, but during COVID, I'm based in Edison, New Jersey.
And I'm Aditya. I'm working at Amazon right now in Seattle in the Prime Video org. I actually just started a month and a half ago, and it is super exciting. So that is where I'm at. We're both Rutgers 2018 CS grads. We're both super involved in USACS as well during our time.
Cool. Any questions? I guess that's not a slide people have questions on. All right. We put our LinkedIns there if people are interested in using these slides after the fact. Cool. So the plan here is that when we gave this talk a couple of years ago, it went two or 3 hours, and we barely covered anything. But since we only have 1 hour right now, we're probably only going to cover half of it, and we're going to cover the half that is more so on your computer. So we're going to talk about the OS part of this and the browser part of this, and then for the follow-up talk, we'll cover the network part of this and the server part of this, which is probably, I'd say, the more complex part of this, because there's just so much that happens that is not intuitive, I'd say. Would you say that, Aditya, as well?
It's harder to visualize on a text-based PowerPoint.
Yeah, like with the OS stuff, you can press a key on your keyboard and you can see like what we mean. But if we talk to you about how BGP works and how it achieves converges to a stable IP forwarding set, like that just wouldn't make any sense right now. Cool. So this talk, we're just going to cover the OS stuff and the browser stuff. For the OS stuff, we're going to cover. So let's dive into that. Aditya, do you want to go into it?
Yeah, so as for what we're going to talk about in terms of the OS is we're going to get from pressing the G key on your keyboard all the way to getting it to show up on your screen itself. And that involves a lot more steps than you might initially think. So throughout this presentation, we want to get through actually what happens when you press the G key, what happens on the hardware that you're running your Chrome on, as well as what happens when the G actually shows up into your Chrome URL bar.
Cool.
So the first thing you'd want to do when you want to go to Google, or the first thing you'd want to do when you open an internet browser is type something, right? So we're gonna start at physically pressing any key on your keyboard, and there's a lot of things going on here. Based on the keyboard that you have, pressing a key can have different levels of actuation, feel differently. So go ahead and press a key on your keyboard and actually take note of how far it travels, or how far you have to press it before the letter shows up on your text box. And there can be different types of keys, all the way from smooth and direct, meaning there's very little force required to activate it, or clicky. You might have heard your friends or coworkers talk about these clicky switches.
If you're not a child,
so for reference,
if you're not a child, you probably remember the old keyboards of the the early 2000s and how they feel kind of like typing on mush or mashed potatoes compared to mechanical keyboards of today, where it sounds like stuff like that,
Yeah, so for reference, if you have a 2016 MacBook Pro, how many of you guys have one? I'm sure a lot of you might. The keyboard only travels zero point 0.7 millimeters on those butterfly key switches, versus the 3 to 4 millimeters of travel that a mechanical keyboard might have. So just pressing that switch alone can make a world of difference.
But so by travel, we're talking about vertical distance that you push down.
Right. And we see two popular switches here that people like to use. I personally use reds, by the way.
I use browns. Red suck. Screw you, Aditya. There's like a fan base for each type of keyboard here, especially if you're into mechanical keyboards. Like the Cherry MX is pretty much like an industry standard, and tons of different types of keyboards will be like, oh, we offer this keyboard in red, brown, and green, or blue, right? If you have blues, then you're probably a really annoying person, because your clicks will sound like we could hear it from a mile away. But if you run browns, you're probably pretty
pro tip if you're
sorry.
Pro tip if you're going to get a keyboard for work, do not get blues. Your coworkers will hate you.
So this is like
anyway,
kind of like
on.
a diagram of like pressing a key and what it looks like. Aditya, do you want to describe it?
Sure. So at the bottom, you have the actual spring that defines like how much force would be needed to push your key all the way down, or so-called like bottoming out. As well as you have the switch itself, which is the little bump at the top, right below the key cap, which is the outermost shell. So you press the keycap down, which pushes the switch down, and you see the little rod underneath the key switch itself, which when it makes contact with the circuit board at the bottom, triggers the what's going to come next, which is the whole OS registering your key inputs.
Yeah, so the key thing to notice here is that you're basically, when the rod goes through the spring and hits the bottom of the keyboard, it's closing a circuit, and that activates an electrical signal that gets sent to basically another hardware device in your computer called a interrupt controller. It's kind of like a microcontroller, it's like a microchip whose sole job it is to listen to these electrical signals from peripheral devices like keyboards and mice, and talk to the OS.
Yeah, and that's the case if you have a keyboard that's like built into your machine, like a laptop. There could also be like a bunch of you with USB keyboards. So in the case of a USB keyboard, there's a special controller called the USB controller, and you plug your machines into the USB, plug your peripherals into the USB keyboard, or USB controller, and it listens every 10 milliseconds for inputs on these devices. But the process is still the same, where whenever a key is pressed, an electrical signal is sent to the IR2, the interrupt controller, and then the interrupt controller sends a hardware interrupt vector to the CPU, which is essentially like an integer representing which key was pressed. Taking this, the CPU then indexes the interrupt descriptor table, or the IDT, and it then looks up which key was pressed, and essentially executes that function, mapping it kind of like a hash map between what was pressed and the function to execute as a result of what was pressed.
So to add on to that, part of system boot up, like when you turn on your computer, the operating system, as part of boot up, you like initialize all of your hardware devices, and the kernel loads the interrupt descriptor table into memory, so that when an interrupt comes in, the kernel can just look up what that interrupt is and what function should be run. It's just some arbitrary code, and then it just executes the code. So like, if for those of you who have taken data structures, just imagine a hash map and you index it by a number and you get a function and then you execute the function. It's basically what's happening, but in hardware land.
Any questions so far, by the way, feel free to ask us.
So a little story. When I was interviewing for a bunch of places, I think as a junior or senior, both of them actually, when I was going for like software site reliability engineering internships and stuff, people would ask me about people would literally ask me this question in the interview, and I would start talking about the interrupt descriptor table, and then they were just like, holy crap, who is this junior? So really, it's not that complex of a process, but knowing about it is like good for interviews. Cool. Any questions? Oh,
Next, the next kind of keyboard. Okay. I guess we can also take questions at the end. So the next kind of keyboard that you might be interacting with is also like a touchscreen on your phone or like an iPad, for instance. So the way that the keyboard on these things might work, there's no like physical key press, obviously. But what happens is when you press your touch screen, it basically closes a circuit by introducing a voltage drop. And the screen controller, similar to like the interrupt controller, they're all things that interact with inputs. This detects the voltage drop and sends a signal, sends a software interrupt to the OS, similar to how the physical keyboard interrupt works. And this makes the mobile OS notify the currently active application or anything that this interrupt happened. So think of it like when you press the screen, the voltage drop happens, which then sends a signal indicating that this happened. The OS then brings that back to the application with what should happen as a result of it being pressed here.
So maybe as a visual aid, so if I have a phone here, right, and I put my finger on it, imagine there's like a grid of just like nodes on the surface of the phone, and when I put my finger on it, the nodes are sending current through my finger into other nodes, right? And so that's closing a circuit, and that's inducing a voltage drop that the screen controller then analyzes and figures out, oh, okay, like it localizes my key press to a particular section of the screen, and does that really, really, really fast. And then sends an interrupt in pretty much the same way to the Android OS or the iOS that's running on your phone.
That's a good way of putting it as well. So same thing happens, except there's no physical key press. It's all closing the circuit, like the key described by you pressing your finger on the touchscreen.
Cool. So moving forward, this is a drawing that I made for Sean when I was explaining this to him a couple days ago, and I thought I would just throw it in here. So let's say there's a person at the top, and they're using a laptop, right? So they only care about the apps that they're using. So they're using Chrome, maybe League of Legends, maybe Firefox, whatever. And assume for this just purposes of this diagram that there's one CPU on the machine. So there's no multiprocessing going on. It's just one CPU. So these applications kind of like how are we running multiple applications just on one CPU at the same time? So it's not actually running at the same time. They're basically given time slots for the apps to run. So from the kernel scheduler. So there's a scheduler that's running in the OS, and it's basically saying, okay, Firefox, you have 10 milliseconds to run. All right, 10 milliseconds are up. Okay, now League of Legends, you can run. Now Chrome, you can run. This is a really simplistic way of looking at it, but that's basically what's happening. If you have multiple CPUs on the machine, then it like pins these applications to specific CPUs so that they can keep scheduling their tasks on the same CPUs every time. Does that make sense? So that's the scheduler part.
Do you want to talk about the analogy we had with the
restaurant? Yeah, well let's get into that in a bit.
With the restaurant, yeah.
I'll talk about the drivers first. So
Sure.
At the bottom of this, right there, of this diagram, there's a bunch of hardware devices like the keyboard, the mouse, the CPUs, the network interface cards. So all of these things send interrupts to the operating system in the same mechanism that we described of like sending an interrupt to the CPU. The CPU looks it up in the interrupt descriptor table and then executes a function which traps into the kernel and tells the scheduler what interrupt it was and which context to send it to. So you can't talk to the OS through a new hardware device without having a driver in there. So think of a driver as a translator for a new hardware device that you're introducing to your friend group, let's say. So whenever you plug in a new mouse or a new keyboard into your machine, you usually see a notification that says installing driver for, or like searching for drivers for this new hardware device, right? If it doesn't do that, it literally can't understand what the heck your keyboard is sending it. So that's why the drivers are there. So during system boot up, when the system boots up, it just initializes these drivers and configures them properly to talk to the right hardware device. That's pretty much what is happening during system boot up. And again, when, let's say, like a network request comes in, right? That's coming in through the hardware device called the network interface card, way on the left over here. And those interrupts are being sent to your OS and being served by your CPU. So all of it is just working on the same exact model of interrupts coming in via hardware devices and then being scheduled via the CPU. And I drew a little interrupt descriptor table on the right over here. So that's, you can imagine an ID on the left, which is an interrupt vector, and a function on the right, which is an interrupt handler. Cool. Anything to add, Aditya?
I think this is a good explanation. And yeah, simplistically, like the interrupt vector, to remind you guys, is what the interrupt is mapped to. So when the CPU sees this coming in, it takes this value to the interrupt descriptor table and looks up what to do as a result of receiving this value.
Pretty much. So you wanted to share a restaurant analogy, although it's.
Yeah, I think you did a good enough job. If we have further questions, we can talk about it.
Okay. Cool.
Yeah.
So again, I want to emphasize that if we have a multi-processor model, so if you have multiple CPUs and multiple applications to schedule on those multiple CPUs, then you can imagine the scheduler has like kind of a difficult job of figuring out what applications should be run on which schedulers. And there can't be any bugs in the scheduler, otherwise like people would complain, right? That would be awful. The general philosophy of OS design is that the OS should be invisible to the user. The user should just be able to click a keyboard and care about the apps that they run. So one thing that actually, this is relevant to some work I do at Facebook. We have like 50 CPUs on our machines, and I run a traffic fleet, which means that we're kind of bound, like the performance of the servers is bound on network load. And so our network interface cards are really, really hot. And so whenever a network request comes in on a network interface card at Facebook, we used to distribute these like interrupts to just a small handful of the CPUs on the machine. And the CPU load, like the CPU utilization on some of the CPUs that were handling the interrupt requests from the network interface card was like 60 to 70%, which is ridiculous compared to normal industry standards for CPU utilization. But when we distributed it to 32 CPUs instead of 16, basically we just flattened the amount of load that we do on all the CPUs on the system. So like that's the kind of work that you can imagine happens in OS land and kernel land to push performance boundaries. Cool. As we said, when we turn up the system, when you press the power button, part of the stuff that happens in the very beginning is that the drivers are initialized. Otherwise, like when you turn on your computer, you notice that the keyboard doesn't really do anything initially. And if you have a light up keyboard like me, or Aditya, you have a light up keyboard, right?
Yeah,
it doesn't light up for like a couple of seconds until after you start it, right? That's because it's not initialized yet. Cool. So now we'll talk about the browser. So we talked about the OS and how it receives interrupts from the hardware devices over the interrupt request line into the interrupt descriptor table. So now the kernel has the signal that was sent, and let's say that a keyboard sent the G key. So you press the G key, and now the kernel has the G key in ASCII. Now it'll basically send it to the active context as dictated by the scheduler. The scheduler will keep tracks of what context is active, what process is active on the screen. A way to think about it is like if you're playing a video game and you like tab out of the video game, you'll see the video game, like the frame rate on the video game, like drop like in half, right? So like if I'm playing League and I'm at like 70 FPS and I tab over to Chrome to like tell my AFK teammate to get back on the game, my frame rate drops to like 15, like 5, 10, 15, right? That's because the CPU is kind of like, oh, this is not the active context anymore. The scheduler is like, this is not the active context anymore. Then I don't need to prioritize it. So I'll give less time to this guy on their CPUs. So that's another thing that the scheduler has to worry about. But in this case where there's just a single active context, that's like a single static active context of like a browser, like Chrome, it can just send the G key directly to that browser. And the browser you can think of the browser as always having like multiple ears open to listen to input from the OS. So if you're more technically inclined, an ear, when I'm talking about an ear, I'm talking about a file descriptor that's always open. And another thing to consider is that. Sorry?
I was going to say, and also the program itself maintains the subcontext, which is like what part of the program are you actually still looking at? In this case, the URL bar.
So if you click on the white space on the screen and you type in G, like nothing will happen, right? But if you click in the search bar and you type in G, like a G will show up. So, that has to happen via some mechanism. So that's more of an application specific mechanism for handling subcontexts. So when you type in let's say something into your URL bar, sometimes you get URL suggestions and sometimes you get search suggestions, right? We'll see that later in the slides, but at this point, what happens is that the URL has to be parsed. If it's a URL, it has to be parsed. And when I say parsed, I mean broken up into 3 components. The first one being the protocol. So HTTP or HTTPS is one of them. If you look at any browser and you just look at the URL bar, it'll say http://, right? So sometimes when you're like downloading a file, you'll see that changes to FTP, which is file transfer protocol. If you're using the darknet, so on the Onion Tor browser, which I don't recommend you do, it'll be a different protocol. It'll be the Onion protocol. If you're just looking at local files on your local file system, it'll be like file:// right? So that's just the protocol that the browser knows. The browser has to follow one of these protocols in order to get the resource that you're asking for. And the second part of this is the domain name. So youtube.com, mail.google.com, cs.rutgers.edu. These are all domain names. And in the second part of this talk, which is going to happen later, we're going to talk about how that maps to an IP address via DNS and gets resolved and all that stuff. The third part of the URL is the route. So like / is the default route, / results. This is website specific, right? So on GitHub, you're going to have like / some guy's username. On Google, you're going to have /search. On YouTube, you're going to have /results. On Facebook, I don't know what the heck you have on Facebook. I don't use the app. Cool. So those are the 3 parts that are relevant for URLs. And we're going to talk about search terms after this. If no protocol or valid domain name was given, so like if the browser could not recognize any relevant stuff there, the content goes to the default search engine. So for Chrome, that's Google. For Microsoft, that happens to be Bing for some godforsaken reason. Anyway, I feel like I'm going too fast. Does anyone have any questions? All right, maybe questions at the end then. Cool.
Yeah. So let's also talk about so let's talk about what happens like when you type in when you finally get that letter G like in your search bar, or like whatever you're searching like shows up in the URL bar. The Chrome engine or any browser engine nowadays shows you like suggestions. Do you want to go over to the last slide real quick so we can show a picture of this?
Yeah, sure.
So like you'll see like a drop down that has a bunch of different results. Some of them will be like some of them will be based on your previous history. Some of them will be based on like suggestions, like coughing, or that's a previous history. But it could also be like a suggestion. It could also be like popular searches if you have no history with the browser before. It could also be based on cookies. So, for example, if you've visited a site before, and you'll see these banners like, by using this site, you accept our cookies, which is kind of like a trace. The website is leaving a trace saying that you visited our website, and here's the data you interacted with on our website. Based on this, the browser can interact with your input and show you suggestions. Like, hey, do you want to go back to this website again? Do you want to go back to look at this this product on Amazon again for any reason? And also, like they can also show you like suggestions based on your location. So, for instance, if you're not in America, your popular searches might not be the same as someone who is in America. Or let's say you visited completely different websites than someone like your suggestions will not be the same as that person's because you'll have different cookies. So based on these different factors, the browser will compute the most relevant things to show you in your autocomplete. For example, we have here on the previous slide, if you want to go back.
Sure.
We have, for example, like Foursquare. They do location triangulation based on like nearby Wi-Fi signals to analyze foot traffic. Foursquare is an application to look at, like kind of like Yelp, to look at nearby businesses and restaurants. I believe, right?
Yeah. So some context around this. So we as part of Hack and Why, we got a bunch of talks at Foursquare. We kind of learned about their business model. So they have like a whole customer facing product, which is like being basically a Yelp competitor. And but the main part of the business that Foursquare runs is location tracking data and their clients are like Google, Facebook, other companies that want location data for users. So Foursquare has a whole bunch of data scientists whose full-time job it is to basically track people in better ways. So it sounds a bit Orwellian, but let's ignore that for now. This is a different talk. So they said they have last time I talked to them, which a couple years ago, which they said they had 27 different signals or ways or like data points that they use to track people's location, given that they opt into it. So one of them is nearby Wi-Fi signals. So if you're in public, let's say you're at the mall and you're walking around, like your phone will have a certain Wi-Fi signal strength to the nearby router at what are some stores nowadays? Zara, like one of the like let's say Zara has its own
Starbucks or anything.
Yeah, Zara, Starbucks, Jamba Juice, Auntie Anne's, like Auntie Anne's. Sorry.
Now you're just describing Menlo Park Mall.
Yeah. No. Anyway, so like you have a different Wi-Fi signal strength to each of these Wi-Fi routers, right? And so these like your phone is going to report that to Foursquare, and Foursquare can use that even if you're not sending your location data directly to Foursquare. Foursquare can use that data to figure out, okay, like they're probably in this general location, and the more Wi-Fi signals they have, the better they can triangulate your location. One of the business impacts of that is that they can track foot traffic as it goes through a mall, and they can like partner with malls, for example, and say that this much traffic is going to your store or this much traffic is going to your store, and malls can take that data and be like, okay, we changed something, like we made our sign bigger, does that affect foot traffic? So that's the kind of stuff that like
that's actually really cool.
At this level. Yeah, it's pretty interesting. And being a data scientist on this stuff, to like, that's just, again, one of 27 signals that they have, which is pretty interesting. And like they show us maps
Yeah,
of like foot
yeah.
traffic in
I
New York as a
didn't know
result
about
of
the
it.
full application of that.
Yeah, it's super cool from a technical standpoint. From an ethical standpoint, it's a little more like, okay, it's interesting. Maybe this should be regulated.
And also one other way that you can get your location is just based on the IP address itself. So the browser or any application can look at the IP address you're connecting to that to it from, and narrow down your geo IP location, like a base location, not like a specific down to the pin location. But these are just some of the ways that they generate these auto suggestions to show you.
Yeah, a lot of IPs you can take and just Google like where is this IP, and you'll find a website that lets you look up, oh, this IP is in Kazakhstan. If you do that if you run a VPN and you do that, you'll find that some strange countries are in there. I want to expand on the cookies part of this. So if you're not sure what a cookie is, your browser, and you have a lot of control over this, but your browser maintains a table of cookies, and cookies are basically like numbers. So numbers that track your session data. So let's say you went on Amazon and like clicked a product, and you were like, oh, it looks cool. I might come back to this later, maybe, and maybe never. And then you like go on Facebook. Now Facebook like has this, like when you go to the Facebook website on your desktop or on your phone, honestly, there's a cookie there, and it tells Facebook that, oh, like they have an Amazon session, and Facebook can talk to Amazon and ask, hey, what is this session? And then Amazon can say, oh, these are some ads that you should show them, and then we show them ads, and if you end up going back to Amazon and buying that product, eventually Facebook will get a commission. That's kind of like one of the major ways that ads makes money.
So if you ever see like products that you like visited before, and then you see that ad pop up somewhere else, there's a very high chance it's because of what cookie you have on your browser session.
Yeah, and you can disable cookies, and you can like delete certain cookies. You can check this all in your browser, but like cookies aren't all like questionable ethically. Like some cookies are pretty much to track like what is your shopping cart in Amazon. Like that's as a result of cookies. Like if you close your Amazon session and you go back to Amazon.com, you'll see that your cart is still there. It's because it saved your session data over multiple tabs on the browser. Oops.
Shopping cart, I don't think they do it on cookies anymore, but I think they do it based on account, because otherwise it doesn't go across devices, right?
Oh, that makes a lot of sense. But they used to do it on cookies, I think.
Yeah, they used to, yeah.
Okay. Yeah, Aditya would be the Amazon expert here, but I'm sure some online shopping services still use cookies.
Yeah.
So another note on popular searches.
You can find out which ones by just.
Yeah.
You can just find out just by removing your cookies, and then if your shopping cart is there, then they use cookies. Or they don't use cookies. Yeah.
Right. Another note on popular searches. So if you are like traveling abroad in Italy, let's say like Facebook or Google will still know that your friend circle is like American tech yuppie, right? So they're gonna target ads towards you based on that profile, and less so on the Italian native profile. But the fact that you are in Italy will factor into what searches are offered to you. I'm pretty sure this happens as a result of ML at this point in time. But I don't know the details. Cool. So as we can see from this screenshot of Sean's computer, he's clearly into video games, Pokemon, and history, and Fire Emblem, and Kingdom Hearts. So like you can tell a lot about a person from their search history, and not like you can imagine how much a machine learning algorithm can deduce as well based on their searches. Cool. I think that's the majority of what we wanted to cover in this talk. We could go into IP addresses if you guys want, but that's stuff we're going to probably cover next talk. Yeah,
I think we should do a high level overview of what we covered. So we covered going from pressing the key switch all the way to what happens to get it to show up on your machine, and then also talk about what happens once it does show up on your machine or your application, how it gets from G to become google.com auto-completed or whatever website you were searching for, without you needing to always tell it exactly where you need to go.
Oh, we missed something. Okay, so we talked about, you talked about GK actuation, hardware driver, software scheduler, interrupts, IDT, context switch. Oh, we didn't talk about context switches actually. So the process of moving from like, okay, Firefox, you have 10 milliseconds. All right, get off. Chrome, you have 10 milliseconds. That process is called a context switch. And context switches are heavy operations to do because the kernel actually needs to like take the running process and like put it to sleep. So they need to unload, they need to save all of its states. So imagine you're like playing a game. And if you've ever like used Visual Boy Advance or something, you like save state and then you can load a different state. So what actually happens is that it's saving everything to disk, or sorry, it is, right? It's saving. No, it doesn't save it to disk. It just saves
I
it
think
to memory, right?
it does save it to disk because you can output that save state.
No, I'm talking about process context switches.
Oh, I thought you were specifically talking about Visual Boy Advance. Never mind.
No.
Yeah.
So I'm pretty sure it just.
It is memory.
So it saves it to memory and then puts it in the background and then says, okay, another process Chrome come up and load your registers from your last save state. And then it starts running Chrome. So that's a heavy operation. So the scheduler tries to minimize context switches as much as possible. And it does that in a way that also doesn't like starve certain processes of CPU time. So when a process is starved of CPU time, that'll look like League of Legends running at 5 FPS. Does that make sense? And another way to control this as a user is by setting process priorities. So you can use this command called nice or renice on the Linux command line. And you can explicitly set that, like, I want Chrome to run at priority like 0, which is pretty high priority. So there's a what's the word? Heuristic. There's a heuristic algorithm to figure out what is the next process that should run on the machine. And it's not just like a simple round robin. It's a little more complex. So that's a bit about context switches. We talked about the browser suggestions, cookies, location tracking, ad commissions, URL parsing. We didn't talk about DOM trees. So when you send your request over the internet to the IP address that we mentioned here, right here. So when you send it to an IP address and you give it a route to give it to, basically you can treat that as a black box for now and assume that some content is coming back in like an HTTP response. Think of that as like a JSON object, or just think of a really long string that can be parsed into a tree structure. The output is basically parsed by your browser as a DOM tree. Who among here has done the DOM tree project in data structures? So Aditya has done it. Who else has done it? They didn't kill the project, did they?
No, I remember doing it for data structures.
Okay.
So spring 2018 would have done it.
Yeah, I did it too.
Cool. Did they kill it after 2018?
Possible. I don't remember helping anyone with DOM tree after I took it.
Tragic.
That's fine because the project was annoying to help with.
Tree.
What?
I don't think we did DOM tree. And I took it last semester.
Yeah, we didn't do it.
Okay. Well, how would you describe a DOM tree, Jonathan or Manya?
It's like so you have HTML for a web page, and it's sort of like the way you can traverse it, where everything is sort of nested within each other, and you have to, at least the way I remember it, you go through and try to like parse out all the different subdivisions in each element, etc., etc. But it's been a while, so.
Why don't you just open up the inspect element and show them the DOM tree?
Yeah, that's what I'm doing. So this is some psychopath's web page, and I'm going to look at their DOM tree.
Some whose web page?
Some psychopath. So this is what their DOM tree looks like. This is just HTML, right? But basically, it's a DOM tree, and wow, he actually writes really neat HTML. That's shocking.
Belly button signature ties.
Sorry?
I'm just reading some of it. It's pretty interesting.
Yeah, he's a really interesting guy. Anyway, so this HTML is rendered as your browser into a data structure called a DOM tree, which is basically a tree structure that has any of n children. It's not a binary tree. It's like n children. It's an n-ary tree.
N-ary tree. Yeah.
Yeah. So your browser takes this and just figures out how to display it on your screen. So it takes this as input and it comes up with this. And if we had Doug on this call, he could probably spend another 3 hours talking about the rendering pipeline for computers.
I think we should go to questions. We have 15 minutes.